Graph G consists of two things. A set V, that means elements are called vertices, points, or nodes of G. It can be symbol, alphabet, or digit. Then A set E is unordered pairs of distinct vertices called edges of G. Such graph is denoted by G VE when both of part of G are to be emphasized.
Relation is related to ordered pair such that if the ordered pair has x, y, then x is related to y through the relation of R. A relation consists finitely many ordered pair of number. We can determine the graph whether it's a function or not a function by simply looking at the out degree of a vertex. From Digilib in a website, it says that the graph of a function f is the set of all points in the plane of the form ordered pair x fx. For directed graph, it is a graph that have direction for each edges, which means that it have an arc, which is the direction of the edges.
Chapter 4, Directed Graph. I take this question from March 2014. Given G, draw a directed graph that represents G. So first you must draw all the nodes A, B, C, D, E. Then given G, AB, AD, AE, BB, BD, CE, DC, DE, and EB. From 1, draw a subgraph of G which consists of all the nodes in G. So just draw all the nodes again, A, B, C, D, E. Then just connect them given G. AB, AE, DC, DE, EB, as well as all the vertex are connected. From 1, determine the degree, in degree, and out degree for each node. Okay, in degree is how many edge that you receive from other nodes, and out degree is how many edge that you point out to other nodes. Like A, it has 0 in degree because all of the edges are pointed to other nodes like E, D, and B. So degree is just in and out combined, and in and out degree must have same total 9 in this case. From 1, state the shortest path from node A to C. A, D, D, C is the shortest path from A to C.
From the question, it states that let R be the relation on M, such as it is more than 1 and less than 10, and also a prime number. Also in this question, it states that ordered pair xy is element of M. Relation x on y if and only if x plus y is more or equal than 8. From the questions, we must extract the important things. We know that M contains number 2 until 9 and also a prime number. We know that from the questions, ordered pair xy is element of M. From the questions, it also states that R is a relation x on y with x plus y must be equal or more than 8. Students must list all the number contained in M, which is 2 until 9 and also prime number. My suggestion of doing this question, student need to list all the possible ordered pair. In order to get ordered pair inside the relation, students must fulfill the condition which is x plus y more or equal to 8. As you can see here are the ordered pair that fulfill the condition, which is x plus y more or equal a. To answer the directed graph, we must point the ordered pair x to y. I take this as an example, which is 2 pointed to 7, 2 pointed to 7, 3 pointed to 5, 3 pointed to 5, 3 pointed to 7, 3 pointed to 7, 5 pointed to 3, 5 pointed to 3, 5 is pointed to 5, which is to itself. So we must use the loop. 5 pointed to 7, pointed to 7, 7 pointed to 2, 7, 2, 7 pointed to 3, 7 pointed to 3, 7 pointed to 5, 7 pointed to 5, 7 and pointed to 7, which is to itself. Once again, we must use the loop. So for question 1, here are the directed graph. So to answer questions number 2, we must look at the graph in order to determine whether R is partial order or equivalent relation. To answer this question also, we must state the properties of relation, which is transitive, symmetric, antisymmetric, and reflexive. From the graph, we know that R is not reflexive. This is because there is no loop at every vertex. We can see that vertex 2 and 3 doesn't have any loops. For symmetric, we can say that this graph is symmetric. This is because there is an edge between x and y and y to x. As we can see, there is the edges between 2 and 7, 7 to 2, 5 to 3, 3 to 5, 7 to 3, 3 to 7, and 7 to 5, and 5 to 7. Therefore, we can conclude that this graph is symmetric. For antisymmetric, we can say that this graph is antisymmetric. This is because there is edges between 2 and 7 to 2, but 7 is not equal to 2. By that, we cannot take this graph as antisymmetric. For transitive, we can say that this graph is not transitive. This is because there is an edge between 2 and 7 to 5, but there is no edges from 2 to 5. So we conclude that this graph is not transitive. From the properties of the relation, we can state that this graph of R is not partial order or equivalent relation.
Subtopic 5.1 Basic Connectives and Truth Tables. In this subtopic, we will learn about statement and some of the common logical connectives. A statement or proposition is a sentence or mathematical expression that is either definitely true or definitely false, but not both. There are 5 common logical connectives that we will learn from this subtopic, such as: first, negation. Negation translated as not or it is not the case that. For example, negation A is translated as not A or it is not true that A. Next, conjunction. Conjunction translated as and or sometimes but. For example, A conjunction B is translated as A and B. Next is disjunction. Disjunction is translated by or. For example, A disjunction B is translated as A or B. Next is implication. It is translated as if, then. For example, A implication B is translated as if A, then B. And lastly, biconditional. It is translated as if and only if. For example, A biconditional is translated as A if and only if B.
Two statements A and B are said to be logically equivalent, and we write A logical equivalent to B when the statement A is true, respectively false, if and only if the statement B is true, respectively false. On the other hand, we can say that two statements A and B are said to be logically equivalent if the truth value for the statement A and B are equivalent or similar. Tautology is a propositional statement that is true for all cases, which means the final value for the truth value will be true for all cases. Contradiction is a propositional statement that is false for all cases, which means the final value for the truth value will be false for all cases. Contingent, a propositional statement that is neither a tautology or a contradiction, which means the final value for the truth value is not all true and not all false. Conditional statement of form P implies Q is associated with three other statements, which is converse, inverse, and contrapositive.
We must determine whether the arguments are logically equivalent or not.
For this question, student must list all the P value which is true, true, false, false. List the Q value which is true, false, true, false. List the negation P value which is false, false, true, true. Continue with negation Q, false, true, and P or Q which is true, true, false. Negation P or Q will be false, false, true. Negation P or negation Q will be false, true, true, true. Therefore, we can state that argument 1 are not logically equivalent to argument 2 because of the truth value are not similar.
Okay, the question is, by using a truth table, determine if the following compound statement is a tautology, a contradiction, or a contingency. First step, we need to analyze what the question wants. We can see that the question wants to know what is the compound statement, as we can see from here. So to determine the compound statement, we need to make a truth table. Okay, first, we need to put the PQR into the truth table. PQR. We need to insert truth and false for the PQR in this order, such as true, 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 false. True, false, true, true, false, 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 true, true, false, true, false, and false, false, true, and lastly is false, false, false. Okay, after that, we need to determine what is the common logical we need to do first. So we need to separate the statement, this statement, such as we can separate like this is A and this is P. A is negation P and biconditional Q. This is A and this is P. P, R. Okay, so from A, we need to solve for negation P first. Negation is the opposite of the original statement, such as this is negation P, this is P. First is truth, so negation P is false. So next is true, false. This is true, this is false. This is true, this is false, 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 false. So this is true, 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 and true. Okay, next we need to settle for the A, negation P, and biconditional Q. Biconditional means if both statement is the same, so it means it is true, otherwise it is false. So negation P, biconditional Q. Negation P and Q, false, true is false. False, true again, false. False, false is true. False, false, true. True, true, true. True, true, true. True, false is false, and true, false, false. So this is for the A. Next part is B. B is B conjunction are. So conjunction means if both statement is true, so the statement will be true, otherwise it is false. P and R, so true and true is true, true and false is false, true is true, false true is false, false true again is false, false is false, false true is false, and false is false. For the final column, A disjunction B. So this is the statement. So for example, false and true means it's true, false and false mean it false, true mean it's true, true false mean it false, mean it true, sorry, true false mean it true, true false true, false false false, false false and false. As we can see, there are some false and true values from this truth table: true, false, true, false, false. We can conclude that the final column of the truth table shows that all the values are true and false. The compound statement is contingency.